beyond the simple harmonic motion. Roughly speaking, we can put all the oscillations into three categories. Okay? One is called the free oscillation. Okay. Free oscillation means there is no external force to make the oscillation. The oscillation is totally controlled or driven by the internal force. For example, the simple harmonic motion, wave is, okay, once you make some initial position and release it, then it's oscillated, the oscillation is driven by the internal spring force. Okay, this is called the free oscillation. Simple harmonic motion is one example of free oscillation. And the pendulum, simple pendulum, after you release it, that's the internal force, the weight, and the tension control the motion. Okay, you are not going to push it, so this is a free oscillation. There is no external force. And of course, when we say no external force, we should exclude the frictional force. Okay, when the frictional force is external force. So, in the reality, the spring or the simple pendulum will stop. So it's not exactly free oscillation. If you want it a free oscillation, it should be placed in the vacuum. Okay, so the oscillation will last forever. So, okay, no driven force, no damping force. Okay. Resistance, we call it damping force. Okay, air resistance or other kind of resistance. So driving force and damping force is kind of like our engine force and the resistant force for the car. Okay, two kinds of force. Free oscillation, you don't have any kind of force, external force. Now, so then we have damped force, damped oscillation. Okay, so this one is basically controlled by the damping force. Okay, without or with a very small driving force. Okay, compare this one. Since you have the damping force here, the amplitude should decrease. Okay, this is called damped oscillation. The amplitude will decrease due to the external friction. And this one, the amplitude is a constant. Okay, it will not change. It will oscillate forever. So this is more or less the real situation we have. Okay, and another important kind of oscillation is called the forced oscillation. Okay, so here it's controlled basically by a driving force. Okay. The amplitude here could be getting larger or getting smaller due to the competition between the driving force and the damping force here. Okay, but usually we would like to consider a situation where driving force is larger than the damping, much larger than the damping force. So the three kinds of oscillation, all of them are very common in our daily life. Okay, for example. when you push the swing to make it move, your pushing force is the driving force here. Without this driving force, the resistance will finally slow down and stop the motion of the swing. But if you keep pushing it, and so you can maintain the oscillation regardless of frictional force. Here, driving force, has a special feature because you are going to maintain or produce some repeated motion. So the force is also applied in a repeated or periodic way, right? When you push the swing, you cannot just push it randomly like this. You have to push it 1, 2, 3, 4 like this. You need to make it some pattern, make it repeatedly. So this is the driving force. Now, for the forced oscillation, it's very important because most of the oscillation is forced oscillation in our daily life. Here, when you have a forced oscillation, you need to talk about two frequencies for the oscillation. One is called for forced oscillation. One is called the natural frequency of the system. What is the natural frequency of the system? So if you let the object go, the object will oscillate it in a free oscillation. The frequency for that free oscillation without driving force is called the natural frequency of the system. That's some inherent property of the system itself. Has nothing to do with external force. So when the swing, if you just pull the swing up and let it go, the swing will oscillate with some particular frequency. Please note that's a particular frequency. It's not arbitrary. It has nothing to do with how high you are going to pull it. That's called the natural frequency. And then once you apply the driving force, so there is a frequency of the applied force. You can push it in a fast way, like this, or push it slowly, right? So this is called the driving frequency of the external force. And so the point here is that for free oscillation, the object will oscillate with its own natural frequency. But once you put some driving force, the actual frequency of the system will be omega d, because it will be controlled by the external force. So it will not be the same as its natural frequency. So, for example, this one, if I just let it go, it has its own natural frequency. This is a natural frequency, right? But of course, if I give it some driven force, I can make it to oscillate in any arbitrary frequency. I can make it oscillate like this, or I can make it oscillate like this. Right? So this is the driving frequency, totally controlled by my hand. So once you have a forced oscillation, the frequency of the oscillation will be the driving frequency, omega d. It's not omega. But the omega here still plays some important role for the forced oscillation. Now, in fact, the role will completely change. The natural frequency now will not affect the frequency of the oscillation. In fact, it will affect the amplitude of the frequency. Okay. What happens is that I said I can give it the aux system any arbitrary driven frequency. I can force it to oscillate slow or fast. Okay. But in terms of the energy point of view, if my driven frequency, if I push the system with a frequency which is very close to the natural frequency, then my external pushing will be very effective. So I will produce a high energy oscillation which has a larger amplitude. If I don't want to do that, I'm just trying to push it in my preferred frequency, omega d, which may not be the same as omega. Then the external driving will not be very effective. So some of the energy will be lost due to the fight between the external frequency and the internal frequency, because they don't match each other. So I'm not going to produce a large amplitude oscillation. Okay, so the amplitude of the oscillation will be smaller in that case. Okay, this phenomenon is called resonance. Okay, basically resonance is that every system has some natural frequency. If the external driving force matches the natural frequency, the system will oscillate with the maximum magnitude. Otherwise, it will take a smaller amplitude. Any question here? So we can have some demonstration here. Now, I'm trying to use this object to control the oscillation of this object. Okay. So the basic idea, I'm trying to start the oscillation of like say this one, and this, of course, because they are connected. Okay, they are connected. So once these objects are in oscillation, it will drive this object into oscillation. So the left-hand side will apply the driving force to the right-hand side. But now, how can we match or unmatch the frequency? Because here for this simple system, the frequency is basically determined by the length. Okay? So this frequency, if I use this as driven frequency, it should match the natural frequency of this one. If I use this as driving frequency, it should match this one, right? This one should match this one for the same length. And we can see if that happens. So we should expect, okay, what we should expect if I move this one. Can you guess what you should
move the other green one?
So my guess would be if I move this one, this object will oscillate with a large amplitude. These two will oscillate with smaller amplitude. Okay? Let's see if that happens. Just need to stop them. Okay, you see that? This one oscillates much with a larger amplitude than these two. Okay. So that's because this driving frequency matches this natural frequency, not this, not this. Okay. Now we can check other one. So this one oscillates most because this frequency matches this frequency. Okay. Similarly, if I make the red one, okay. So this is resonance. When the driving frequency matches the natural frequency, you can make the largest oscillation. Okay? And this one has a lot of application or consequence. For example, when the armies, when they marching through a bridge, they should do one important thing. You know what important thing they have to do? They have to stay in a random way. Okay, they cannot keep the same pace. That's because sometimes if they keep the same pace, they kind of put some driven force to oscillate the bridge. If you are very unlucky, the driven force, the driven frequency match the natural frequency of the bridge. It's possible. Okay, the bridge will collapse. Okay, it happens in the history. So after that, we know that when you cross the bridge, you have to be careful. But of course, if you just one person walk along the bridge, that's not a problem. But if the whole band or whole army walks through the bridge, that's a problem. And another application is not application, consequence. Okay. Probably you know some of the soprano, they can break glass with their singing. Okay? But please note that that's not because their direct shock wave to break the glass. Okay? Because only female singer can do that, but not the male singer can do that. If it's a direct shock, the male singer should be able to produce a stronger shock wave. In fact, it's due to the resonance. Because soprano, the female singer, they can sing very high pitch sound. Okay, the frequency of the female voice is much higher than the frequency of the male voice. So it's possible, in some extreme case, the frequency of the female singer, soprano, can match the frequency of the glass. So the glass will shake with a larger and larger amplitude, so sometimes it can break. Okay, so it's just like this. If I give it some, for this one, say this has a high frequency. If this is glass, this is the frequency of the singer, so it will oscillate larger and large. Finally, it can break. Okay, so that's the resonance, and you can see a lot of different application there. And there is a Chinese story telling from a monk, Asian monk, about resonance. It's recorded by some monk. You see, there is a monk in his temple. They have big ring, something like that. Okay, and someday the rings, the bell, you have big bell. The bell rings automatically. Okay, so the monk gets scared, and every day, same time, it will ring automatically. Okay, so the monk gets scared. He thinks that maybe some weird thing happened. But later, a scholar come to visit. One of his friends, a scholar come to visit, and the monk told the story, told this to the scholar, and the scholar think about that, and he did one thing. He just used something to break a small part of the bell. Okay, so change its shape, and then the automatic ring stopped. So you can expect what happened. In fact, it happens is that for some reason there is some other oscillation outside of the temple. Okay, and that frequency matches the natural frequency of the bell. And what the scholar did is to change make a small break for the bell, So it changes the shape of the bell, so it changes the natural frequency of the bell. So it will not match the external driven frequency. So the resonance stops. Okay. Now, so we finished the oscillation. Now we're going to start talk about the wave, which is closely related to the oscillation. Wave is produced by the oscillation, or you can say that wave is the propagation of the oscillation.